spaces. So, I mean, the values here have just switched from NO2 to particulate matter. And here, actually, it gets even worse because out of the 4 centers in Glasgow, only 2 actually have capacity to monitor particles. So if you ever get any data for particles for Glasgow, it comes from only 2 places. So if you think about the entire city and how much data you get, it gets even worse. But we are proposing to use capacitive detection for particulate matter monitoring because it has an advantage to be miniaturized. So it can potentially be made smaller and smaller and smaller and smaller. And how does this work? When particles come into the active volume space of charged electrodes, they increase the capacitance of the electrodes. And essentially what happens is that it displaces air in its own volume, and then by implication increases the electric constant of the space. Yeah, and this results in the increase in capacitance. But for small particles like PM2.5, which are known to stick to the surfaces on which they are deposited, we can have a system like this if we want to do a continual monitoring, where basically we have a staircase detection model. So we have continual particle deposition on the same surface, and then that basically uses the staircase measurement method. If we can find a way of removing the particles, for example, say if we combust them off, like burn them off, then we can have a simple system where you have single signals, and then we can basically recover that and repeat the process again and again. But this method actually gives us opportunity to monitor particulate matter. So we designed essentially a model using COMSOL Multiphysics, and the boundary conditions were specified as, for example, non-slip at the walls, which is understandable, laminar flow through the chamber, which essentially means that the fluid flows in layers that don't interfere with one another. And also we set up conditions of internal walls, and as you can see, this part of the model is specified as a heater. And just for information, the simulation was done at 100 degrees Celsius for this heater. So as the system goes smaller and smaller, there's a possibility to reduce the temperature required and then still achieve similar results. Then the inlet essentially requires a control flow. So in this case, is a velocity flow, so 0.2 meters per second. And the other good thing about this at this macro big level is that we could 3D print the housing. The figure on the right just basically shows us the forces that act on the particle as it goes through the chamber. We've got the drag force, the thermophoretic force, and then the force due to gravity. And the resultant force essentially shown there. Here is the meshing system. We've used a fine mesh to ensure that we can minimize errors as much as possible. And on the bottom right, you have the equations, the equation of continuity, equation of conservation of momentum, and so on, and the particle equation of motion as well. So what are the results that we get? So after simulating these, first of all, the simulation goes such that we do, first of all, coupling between CFD and heat transfer essentially to find the velocity, the pressure, and the temperature profile of the system, and then you then simulate, you couple that result with particle tracing model. What that essentially does is to use the values of the velocity and the pressure and temperature that you've gotten for all the points in the system, and then tries to simulate again and get the particle trajectory at those specific points. And then afterwards, what we've done is to then use those results essentially to simulate a completely different electrostatic system. So basically, we then created a capacitor in the model, and then brought these particles to those specific points, essentially close to the electrodes, and then measured the capacitance that was detected. If anyone has any question on that later on, you can ask. But this is the result that we get. You can clearly see the bending profile here as the fluid essentially flows on top of the heater. So you can see that, and then the streamline here also shows how that also happens. This essentially tells us that thermophoresis essentially pushes up on the fluid flow. And the particles, given that they have different sizes, in this simulation we have used exactly the same particles, but different sizes. So essentially they rise to different height levels within the system. And then we position our detectors, which is capacitive detectors, at this point here in this system and here, basically to intercept. And if you recall, I said earlier in the talk that PM2.5 is known to stick to whatever surface it collides with. I mean, there's a paper on that shows that even after applying like a pump, so to speak, to try to remove the particles, not a lot of it is detached from the particle. But here, what we see here is a temperature profile of the system, and you can see essentially above the heater you have like a drawn out heater profile, essentially because of the flow of the air through the system, and then the heater profile, which is supposed to be uniform on top of the heater, but then is drawn out because of the flow. And the implication of that is that we can then see that when we subject these to different particles, PM2.5 and PM10 in this case, the particles were 2 micron diameter and 8 micron diameter, we can see that when they flow in, first of all, in the same, in the same stream, you can see them begin to separate as time goes on, yeah. And here and here, so PM2.5 is essentially, PM10 is essentially collected here because it doesn't rise as much as PM2.5, and that goes above and is collected here. So I've got a small video animation to show this. And this is essentially, so these are all like snapshots from these, this video, showing exactly how the particles are collected. And this is an advantage over methods that are essentially purely inertia-based, like virtual impactor and the impacting systems, because they still usually have like minor and major flows where you have particles of different sizes mixed within the flow in the different collection areas. Then, like I said earlier, we did the capacitive detection for that, and we essentially moved the particles to be only as close as 3.5 microns. Of course, because the particle diameter is 2 microns, and we didn't want a situation where the position says one micron, and then that would mean that the particle already interferes or say penetrates into the electrodes, which doesn't happen in real life. So we only did up to 3.5 microns above the electrodes, and then move the particles away from there using particles of different permittivity, relative permittivity, and we can see that as the particle moves away from the electrodes, the signal we get essentially reduces, it drops, and we then compared 2.5, 25. We then compared electrode widths of 1 micron and electrode widths of 25 microns. We just wanted to see the effect of increasing the electrode size, the dimension, and then we can see that by increasing the electrode width, we get higher signal levels, obviously because the field is higher. But then this system is a bit complex in that there is an interrelationship between the gap, the finger size, the height above the electrodes, and we will see as I go on how these interrelate. So here, what we've done here is to compare different inter-electrode spaces. So basically, these are the spaces between the electrode fingers. And we can see that as that increases, the capacitance measured reduces for all finger lengths. So that reduces, and we can see that even as the relative permittivity increases further, the other thing we notice is that the capacitance is relatively becoming independent of that. So essentially what this means is that as you go higher than, say, 17.9 microns above the electrode surface, you don't see any signal again. But even at 17.9 microns above the electrode surface, the measured capacitance is essentially independent of the relative permittivity. So the relative permittivity is beneficial while the particle is as close to the electrodes as possible. And this also explains why the collision method, which is the deposition method, is the best instead of having an inflow detection. Because one of the things I think people have tried to do in the past is to have an inflow detection model where instead of forcing the particles to deposit on the electrodes, you just make them flow above the electrodes. But you need, if you wanted to design such a system, to be able to make the particles flow as close as 3.5 microns above the electrodes without deposition, which can be hard. So the last thing that I will be talking about here is just how we have compared the results with literature to verify that this model actually works. And as you can see here, the trend lines are essentially the same, showing that the results agree with literature. I think that's all I will mention. Yeah, finally, this one is just on the fabrication routes. So we've made a few prototypes, and as you can see here, we've fabricated the electrodes on top of carton material, and we are now exploring even MEMS scale integration of this system. But the potential applications, as you can see, is in automobile systems, where we can either put this maybe before the filter or after the filter, and it gives us quite informative measurements, and also in enclosed spaces, so air conditions in the house, for example. And the advantage of this, like I said in the previous talk, is the fact that air quality within the car can be very much influenced by what kind of circulation system is in use. There could be a lot of collection, and also you want to check how well the filter in the car is performing. And also in the house as well, depending on the air exchanges, how often you open the window and close it back, you may want to also monitor these levels. But yes, these are the fabrication routes for this device. And we know that in MEM scale, we have the advantage of reducing capacitances that we have witnessed in this scale. And this will help to realize our dream of having a miniaturized capacitive particulate matter sensor. So with this, I'll just acknowledge everyone who's contributed one way or the other to this project. Thank you very much for listening, and I'm happy to take questions.